So we're going to take the idea that we talked about in the last video of evaluating limits using tables to look at now a specific function rather than a generic mystery function. So I'd like to evaluate the limit as x approaches 0 of 1 over x squared. And now you might say, in this instance, you might say, well, I'm going to outsmart Mr. Huber and say, I'm just going to plug that number in and we'll see what happens. Here we've got 1 over 0 squared, which would give us 1 divided by 0. Remember, one of the biggest things we're not allowed to do in math is divide by 0, which would mean that this is undefined. And we said in the last video, if you end up with something like 1 divided by 0 or 2 divided by 0, that limit does not exist. And that's still technically true. This limit does not exist. But there's a little bit more we can say about the behavior of this function as we get closer and closer to 0. So I'm going to use this method of using tables to help me evaluate this limit. So just like last time, I'm going to look at the left-hand limit and the right-hand limit. We've got to think about both of those. So I want to start with the limit as x approaches 0 from the left-hand side of 1 over x squared. And I'm going to think about taking numbers that are close to 0 on the left-hand side. So if you need to, we can kind of build a little number line here to help us. We can say, okay, there's 0. Maybe -1 on the left-hand side you might think is a good place to start. But for me personally, -1 might as well be a million miles away from 0. I like to be within 1 decimal place of it. So rather than -1, I might say, how about -0.1? And we're just going to move 1 decimal place closer each time. So let's start with an x value of -0.1. Now I'm going to take that number and plug it into my function and then see what y value do I get back. So if I were to take -0.1 and plug that into 1 over x squared, and now we can use your calculator to help us out here, we should end up with a y value of 100. So this is really what we're paying attention to. What y value are we getting closer and closer to? So there's our first step, but one value by itself doesn't really mean anything. Let's get a little bit closer. How about we take an x value this time of -0.01. We'll move within 2 decimal places. So if I were to take -0.01 and plug that into my function, I'd have 1 divided by -0.01 squared. This time when we plug that into our function, we'd end up with 10,000. So we have a much larger y value this time. Okay, I sort of see the behavior, but I always think having kind of 3 steps in here, getting within 3 decimal places is really a way to convince yourself. So I'm going to move 1 more decimal place. I'm going to use an x value of -0.001. And again, just like last time, we're going to plug that into our function. And if we do that, if we plug that into our function, we're going to end up with a y value of a cool million. So if we look at our y values here, we've got 100, 10,000, a million. Our y values seem to just be getting larger and larger and larger. And that's true. That's actually exactly what's happening. If we were to move even closer, if you wanted to take a different x value, like say -0.0001, you could plug that into your function and you'd get a number that's even larger than a million. So this limit does not exist because we're actually not getting close to one particular number. Because if you pick a particular number, you might pick the biggest number you could think of. You might say, how about, a trillion? A trillion. So there's a million, there's a billion, there's a trillion. You might say, okay, that's the biggest number I can think of. But if you move a little bit closer, if you take an x value that's even closer than the one that gave you 1 trillion, you're going to be able to get a larger y value than a trillion. You might get 2 trillion or 10 trillion or 100 trillion. So we can't just pick one particular value. We can always make our y value bigger than that. But I'd like to be able to describe the behavior here. I'd like to be able to tell the reader of this kind of what's going on here. Why doesn't this limit exist? Well, if our y value just keeps getting bigger and bigger and bigger, we would say in this case that our limit is approaching positive infinity. So we can write it like that, or you can write it like this, depending on, I always thought writing it as like a sideways 8 was difficult. So if you write two zeros next to each other, that'll work out. So here our limit from the left-hand side is positive infinity. But we wanted to know what the two-sided limit was, so we need to check the right-handed limit as well. So let's go check that side. So here let's look at the limit as x approaches 0 from the right-hand side of, again, our function 1 over x squared. So if we go back and look at our number line here, we might say, well, positive 1 would work, but again, I like to be within one decimal place, so I think 0.1 would be a good place to start. So if I take an x value of 0.1, and again, we're going to plug it into our function here, 1 over x squared. So we'd have 1 over 0.1 squared. If we plug that into our calculator, have that help us out, we should end up with a y value of 100 again. Okay, we maybe want to move a little bit closer this time. How about a positive 0.01? So an x value of positive 0.01. And again, we're going to plug that into our function. 1 divided by 0.01 squared. And this time we're actually going to end up with 10,000. And here, this function has a special property that because we're taking numbers on opposite sides of 0, we're actually ending up with the same y value. We should say, hey, we've got the same y values here. So if I take 0.001 and plug that into my function, I'm going to end up with 1,000,000 once again. So in this case, again, our y values are getting bigger and bigger and bigger. They're not approaching one single number. They're just getting bigger and bigger and bigger. They're growing larger. So we would say that our limit here is, once again, positive infinity. So if we look at the two separate one-sided limits, we look at the left-hand limit, we said that was positive infinity. We look at the right-hand limit, we said that was positive infinity. So using what we know about limits, we said if the left and the right-hand limit are the same, then that means that the two-sided limit should also be positive infinity. So that means that this limit is positive infinity. Now, be a little bit careful here. I will offer a word of caution. When we talk about infinite limits, when we end up with these limits that are either positive infinity or negative infinity, because we could have a negative case as well, those limits technically do not exist. But we want to be as specific as possible. So it's not enough just to say that that limit does not exist. We want to be able to say, okay, this limit does not exist because it approaches positive infinity. So if you were to say this limit does not exist, sure, you're right. I'd give you partial credit on that question. But I want you to be more specific because we can say, well, it approaches positive infinity or negative infinity. One last thing that I wanted to show you real quick, if you were to graph all of these x and y values on your xy coordinate axis, what's happening is we have maybe here 0.1, here's 0.01, here's 0.001. They're just getting larger and larger, and as you get closer to 0, the y values are going to get larger and larger. We have something that is going up like this. Same thing, same behavior is going to happen on the right-hand side. As we move closer and closer to 0, our y values are growing larger and larger and larger. What we have right here is a vertical asymptote at x equals 0. And we'll talk more about that in this section. You can see the notes that are posted for an actual definition of a vertical asymptote, but hopefully that sounds familiar. We are going to be talking about that more throughout this section.